Hey Cheryl, can you hear me? All right, so you're the only one here. Can I get your pay number? Yes, your ID number. So you were asking about source transformation, right? Right, so multiple sources. Are you comfortable with source transformation in DC? Let's try a source transformation circuit with DC first, and we'll change it to AC. Okay. If you can find a question in the book, let me know. I do have a PDF somewhere of the book. I'll look it up, and we can solve that as well. So I'll start. I just looked up an example of DC online, and we'll start with that. All right. So source transformation. Can you see the screen? Is the screen fine? All right. We have a circuit with a resistor here, current source here. One. Okay. Source. Voltage source. So open circuit. 1200 ohms. Here. 600 ohms over here. Source is 2.8 volts. Plus 2.8 volts. This is 9.5 milliamps. Right? My writing is huge. Can't fit it in on. Okay. So what we need to find is the voltage across this point. Right? We can do it one of two ways. We can transfer the current source into a voltage source, or the voltage source into a current source. All right, let's try turning this guy into a current source. So this goes into over R. So 4.8 over 600. What does that come out to be? There's a calculator. So that's 4.6 milliamps. So this will become this changes into current source going this way. I believe so. Right. Currents in parallel we should add. This way. That seems to be correct, right? Right, I'll, just in case, we'll Google it. So yeah, current will move to the positive terminal of the voltage source. And they're going opposite ways. So that's the one. Okay. Then next we can do what we can do is add the current sources. 9.5 is going up. 4.67 going down. So we subtract from there. Total, I total 4.67. What does that give me? So 4.83, yeah, 4.83 milliamps. Is it going up or down? Yeah, that's correct. Up, yes, going up. So we'll combine the current sources. Here, this. Going up. And now we can combine. Since these two resistors are in parallel, the voltage over here, say the output, that's going to be the same over here and here. So it doesn't matter whether or not you combine these two resistors. You can do resistors in parallel, it's product over sum. You can do that. So if you don't want to do that, you can also do current division. You can find the current through either one of them, and then find the voltage as well. You can do current division. So you're trying to find the current in this branch, it's 1200 ohms. Say it's I2. I2 would be equal to the other branch goes on top. Are you in the 200 Alright. Can I have your A number?
8, 20, 16, 40. 2016 408. 2016 408.
Alright. So what we're doing is, we're doing source transformation. First I just showed how to do it without phasers, so in DC. And next we'll look at phasers. This one comes out to be 1200 plus 600 times the total current. That's 4.83. Whatever that comes out to be, say that's I2. And then the voltage across this part is going to be VO equals 1200 ohms times I2. So that's this problem. Next we can look at one with phasers. Question? Curve. Curve? Yeah. Do you have any problems coming in that you want to go over?
Well, the homework that we did already, some of it we already took it. So, I guess we need to do it.
You can also turn it in for half credit later. So I can go over this weekend, but I can show you this thing.
Okay.
Because of that. So if you do the book,
Yeah.
right, find the problems you want, and after we're done with the source transformation, we'll work with the previous homework. Now with phasers, let me look up a problem online. I'll look it up over here so you can see what I'm doing. Look it up on the computer. Okay, they gave me the same thing. Let's do this single source. And that's in DC. Some alternate dynamic. It's not really a source transformation. Oh boy. Here's one. Okay, let's try this one. Alright, so we have all that good stuff. What it's asking us is to find V of t across the inductor over there. And we have two voltage source, a voltage source on the right and a current source on the left. So what you can see about, Cheryl, can you see both documents up there? Yes, okay. So, so what you notice is with the current source, that resistor is in series, so you can't do a source transformation with the current source over there. But you also notice these phasors, the current source being 6 cosine of 90 amps, and the voltage source being cosine 90 plus 30. The frequencies are the same. The frequency over here is 9 and the frequency over there is 9. They're the same. We can write it in terms of phasors. Yeah. 1 ohm. Write it as 6 and 0. Inductor. Another resistor over there. It'll be 430. This is also 3 volts. Now if you had an inductor or a capacitor over here instead of a resistor, the calculation would be more complicated, but here it's still simple. 1/3 Henry. Now if you transfer that Henry into the phasor domain, I think I'm right in saying that, it'll be J omega L, which is 1/3. The omega over here is 9. We have 3J. So 3J. If you do the source transformation, you have the voltage source and they are in series. So you can transform it into a current source. I equals to V for R. That equation can do 430 over 3 turns into a current source. Once you have a current source, you need this. Okay, so this was plus is up, so it's up. We have a resistance over here. 3 ohms. And that is 3. Okay. What can we do? they doing? Some J3 on that. Yes.
So, because it's voting share,
Mm-hmm.
you made one, we need to do a project.
Okay.
We only did that. You didn't do all of it.
No, I did the right side with this part and transferred into a current source for that.
Oh,
Right. So these current sources are in parallel, but you can't quite remember if this, when we add the current, if that resistor over there is going to make a difference. Let's try that. So, see what they did. That's the same thing we did over there. Okay. What we can do next, we can have these two are in parallel. We can turn them into one inductance. Let's find the equivalent inductance for parallel, we do the 1 over thing.
oh,
So 1 over the that's the 1 over the 1 over the 2. Or we can, for two of them, we can do product over sum. C total is in the print centering of this. This is off center. Looks right. Sorry about that. Okay. Equals to product of the two, that's 3 ohms times 3J product over 3 plus 3J 9J over 3 plus 3J equals to, let's stretch this out. That's not helpful. Okay. I want to tell 9J over J equals to over Are you guys comfortable with this conversion? I'm just bringing the J to the top. So to do that, you multiply with the complement. So if there's a plus here, so you have to multiply with negative, right? That goes to be J plus or zero. That gives us sorry, for the previous one. So what we're doing here is those two, one inductor and a resistor in parallel. You do the combined impedance. To find that, that comes out to be 9J over 3 plus 3J. Just so that the J is on top, take the complement or conjugate. Get the conjugate and multiply it up. Okay. You have E over 2J plus 1 or so now that we have that, because of this resistor, we can't directly add these current sources, and that's why we had to combine these. Now we're going to try to turn this one into a voltage source. Okay. So you have a current source in parallel with an impedance. That and do voltage source. Yeah.
That helps.
Yes. That should help us.
They have current over there.
Yeah, we can do that. Then we'll transform again. So I think this will be a complicated enough problem so that you won't have a problem dealing with this.
I just want to understand. So because we can't add the two currents here because it's something in the middle of it.
Yes, this resistor over here that prevents us from adding the two currents.
Okay.
So what we're going to do is transform this into a voltage source again. See if that helps. If it doesn't help, we'll do another source transformation. So V equals to Ri, or in this case R is V. Let's do Di plus 3 over 2 J plus 1 times 4 over 3 T. Please cancel. 2 it was 30 in terms of IOJ, JM, real and imaginary. So, each plus 2, we have this 2 plus 1. Equals to that'll be equal to 2 parts over 2 35 degrees. That comes out to be 2 So when multiplying these two add, okay, there's the angle to add. Okay. Are you good with this, Cheryl? Okay. Next, we have just found the voltage source. So let's scroll up. Created a voltage source again. This goes away. Yes.
How did you find out how that? How did you transform?
So the question was, how do I transform J plus 1 to 45? So the conversion goes something like this. So you're transferring J plus 1 into the modulus and angle, right? Yeah. To find the modulus, you do, this is 1. So 1 square plus, this is 1J, so 1 square. And when you find the angle, it's tan inverse of 1, the coefficient of J over the coefficient of
I feel like I know more. Magnitude.
We're finding the angle. That's
Yeah,
the magnitude.
like the hypotenuse.
Yeah, totally. Yes.
And then we just, okay, got you.
So we have,
Right there, I got it.
so we have another voltage source again. The spacing out source plus times. We have an impedance over here. Same two impedance as before. That'll be Q over 2. Right here. And the voltage is 2, 5 degrees. Really hopeful I'm right. Alright, now we still can't do anything from here because the sources are not the same. We can't add or subtract or anything. So what you're going to do is add those impedances together. This resistance and that impedance together forms 3 over 2J plus 3 over 2 plus 1. I think even for me, I'm writing J first, then the real part. I think that's bad practice. Usually we write the real part first, then the numerical part. That makes it easier. That's 2 over 2 plus 5 over 2. That's the impedance over here. Yes. Yes.
So what was current resistance? What's that?
Yes. We times it with 3 over 2. So the 3 cancels.
Oh, you keep the 3 over 2.
Yeah.
And then you just add the
We add the angles and we multiply the height.
right. So when we got the 45, we got the 2 the square root of 2.
Yeah.
And so that's just act like that multiplier with 2.
Yep.
Okay.
So that square root of 2 comes from this part.
Right.
We already canceled out 3.
Oh, you still keep, but you still multiply the 33.
Yeah.
3 over 2. Oh, okay. I thought you just did that. Okay.
Alright. So that's the impedance we have, 3 over 2J plus 5 over 2. And we have the voltage source. To get the current source, we'll turn this to the current source again. So we can add finally. To get the current source, we'll do source. over 2 plus E over 2J. I'm doing this inverse E over 2 over I over 2. What does that now be? This bottom part? That part,
Okay, yeah, I was thinking. Square root of 34.
and this is,
Times, tan.
no, but I just find
Oh, right.
that's tan inverse of 3 over 5.
Thirty, 30.96.
Alright, can you do this part 2 root 2 over square root of 34 over?
Four times square root of 17 over 36.
Square root of 17 over 17. Okay. That's the holding source. That's the current source. Okay. That's that. That's okay. Okay. Now we can add the currents and combine them into a single source.
Okay, and then we do that because one thing is,
Yeah. And since it's in parallel,
uh,
we need it to be in parallel with the current sources.
and if we record it, we need to be, now,
So adding the currents.
okay.
we have to turn it into ij. Will be this part times cosine of this plus 6 plus j times sine of this part times, this will be,
You do cosine and sine.
yeah. Cosine 44.4 plus 6 plus j sine j times 4 sine of that angle. To do that, that'll be your current source. Then you can find the voltage across this guy. But that solved the problem. Okay, that's it. Okay. Then once you combine the two current sources, you can find that's the sum of them. That's the total current going through the impedance. So the impedance times the total current will give you the voltage across this. But the thing is, the question asks for the voltage across the inductor in the middle.
Yeah.
This will not give you the voltage across the inductor in the middle. Why I did this entire method was to show you source transformation. That's how you would do source transformation.
Yeah.
But with the original question, the original question, you have to find the voltage over here. What you need to do is, once you have that voltage source transformation, you can do superposition. Are you comfortable with superposition? Yes. Cheryl, are you comfortable with superposition? Right. So with superposition, what you do is first, let's go to a new page. Superposition is when you turn one off, as we just said. We'll take scene 1, I guess, or mode 1. We have a resistor, inductor, Cheryl, did you understand when we did the source transformation? Are you comfortable with it now? Okay. So with source, first what you have to do with this one is turn one of the sources off. Where's my question? That's not it. Okay. Okay. So to turn a current source off means in this branch over here, you can't have any current. The current should be equal to 0. If you want to turn it off, you disconnect it or you open circuit it. Once you open circuit it, there's no current going through this branch over here. So find Vt to the Vt prime, because this is not the actual Vt. You can find that by, you can ignore this, because since there's no current over here, it's not taking any voltage. So there's no voltage across that either. So you can ignore it completely. Ignore this branch, then you have 4. Is the same question? The frequency is different. Okay, so then we'll do that. We'll consider one frequency at a time. This is 430 degrees, right? And this inductor is 1/3 Henry. It's 3 ohms. So what you do is convert this into the J form, to the J L, 1/3 to omega. This time is 3, so 3 J. It backwards. J omega L. That cancels, so you only get J. And then you find the voltage across the inductor, V of T, by doing voltage division. That'll be V of T prime, that equals to the branch that you're finding the voltage across that goes on top. That's J. And the total goes in the bottom. That's 3 plus J. And that's times 4. For time's sake, let's keep it there. Let's not calculate it out. Let's do the next part. For the next part, what you do, this is say scene 2. What you're doing is we draw the same circuit, inductor, current source. We're going to turn off the voltage, which means the voltage across this part has to be 0, and in order to do that, we short circuit. Exactly. So we're going to short circuit this, which means there is current going through there, and there is no voltage. This is still 3. This is going to be 1, and this is 1/3 Henry. The difference this time is this is 6 and 0, but omega this time is 9. So when you find this and do J omega L, find that it's J times 9, that's 1/3, goes to 3J. Right? That's 3J. Now you still have to find the voltage across that, across this part, that is V of T. So even if you combine, you'll notice that the voltage V of T across the inductor, it's also the same voltage across this branch, across the 3 ohm resistor. So there's no problem if you combine these two, because they have the same voltage going across them. So if you do that, they are in parallel, since they have the same voltage, and you'll find Z by doing this. Well, that's 3 times 3J over 3 plus 3J. Once you find that, find Z, the voltage across this combination. That's V of T, say double prime. V double prime. That looks like derivative. So I'll do V2 of T, that equals to Z times I, the current going through it. Once we combine these two, that'll be one branch. So the current that goes here is the same as the current that goes through this entire combination. So once we combine the resistor and the inductor, they're in series. They're still in series, but this is a combination.
Right, okay.
So, and these are in parallel. So if you want to do individual branches,
Okay.
there's current division.
Right.
You don't have to do that
Right.
because we're combining those two,
Yeah.
and the combined impedance becomes Z. And once you find V2 of T is Zi, so you already know the I is this, and the Z you just found out is the combination. Whatever this comes out to be, is Z. Once you find that, you know V2 of T and V1 of T. So after that, you're still not done. You have to find the total voltage when they're both online. So none of them are disconnected, they're both there. So what you do to find the actual V of T, that is just going to be equal to, that's going to be equal to V1 of T and 2. So whatever you found out V1 and V2 to be, and you just add them, and that is superposition. Is that clear to show? Does it make sense? You lose me somewhere, let me know. Okay. All right. We have 5 minutes. If you can take a look at one of the couple of views somewhere, and I don't know if we can solve it in 5 minutes. But was this helpful with you?
Yeah. Yeah. This is not I did this. I took this homework already. I don't make that.
Cheryl, up next we're doing 9.12 from the book. That was a homework problem, I think. So it's saying x equals to 440 and y equals to 30. Okay, so the first question is asking, okay, x plus y times x conjugate, so that's going to be 440 plus 80, 30, and that's going to be 4, and there's a conjugate, negative 40. For this addition part, you take it, turn it into the IJ form. That I feel that easier. When the professor does it in class, he has it.
Instead of like, boom.
He has it. No, he just left it down.
You have to put the after now.
He doesn't really. It takes a lot of time to actually break it down.
Yeah.
440 would be 4 times cosine of 40 plus j sine of 40. This is 4j sine of 40 plus 20 sine of 40 plus 20 j sine of not 40, it should be negative 30 and negative 30. Whatever that comes out to be. times 4 and negative 40. Say it comes out to be, just guessing, be 10 and 70, just a random guess. And that's times 4, 40. So with that, that'll be, you add these, because it's a product, you add the angles, and you multiply this magnitude. X minus y conjugate, that's the next problem. Conjugate. That is going to be, you know x, you know y. Once you have the answer, so it's a and theta. Conjugate that, so it will be a minus theta. Angle here. That's going to be the answer. Third one, x plus y over x. We already did x plus y in the previous problem. That comes to be, say, a and theta degrees over x is 4 and 40. It's going to be a over 4 and theta squared. That's it.
Actually, we also multiplied x. So not the final answer A.
Yeah.
The answer right. Because A was x plus y times conjugate of x, right?
This one?
Yeah.
Yeah.
So we wouldn't take the answer for A. We take like that answer of that parentheses right
This?
there. Yeah. So the rest of them, I mean, to do B and C.
Yeah, you can, this, that's this part, yeah,
Right.
for here, for this part. That one is the same as
Right.
this part, over this comes with 3.
Okay.
So you can use that. And for other problems, email the numbers. I'm prepared. And it's the next session, Friday, 9 a.m. Depending on the course, how do you maybe go over the same things, or maybe
I'll be there.
all right. Okay. Hey, thank you for participating, Cheryl. Thank you for coming. All right. Come to all my sessions. They're excellent. Save this. And
Well, the best way is just practice this a lot, right? I guess.
yes. You can go through book examples. They're usually helpful.
The problems are so long, like we only even do that many in an hour. So it's kind of hard to, when you try to practice it, you spend a lot of time and you're like, how we did this problem?
Yeah, what really throws you off is when you do a problem, then you look at the answer, it doesn't match. But even in the exam, if the answer is not correct, your process is correct,
Right.
then you get points. Usually the answer chances are to be wrong just because you may have input something wrong in the calculator. So don't worry about the answer. Because that takes a lot of time to figure out. Because these are very long
Try to
problems.
focus on like the process. Keep working at it.
Yep.
Because-